I just heard recording progress. So it just started now, the recording?
Yes, I forgot to start that.
Okay. So there's no motivation. We're going straight to a very technical computation. There's great reasons to look into it. So here's the computation. So we're interested really in massless scalars for the case of cosmology because they survive the redshifting, the extreme redshifting of inflation. But this is what we can do for now. We're going to look at conformal scalars, but now we're going to relax the symmetry assumption. In particular, we're going to look at generic, almost completely generic FLRW cosmologies. We're going to look at power law cosmologies. So here it is. Instead of ordinary de Sitter space, we're going to have power law cosmology controlled by a parameter, an exponent epsilon. So in fact, a lot of interesting cosmologies are captured by different values of epsilon. Epsilon equals 0 is just de Sitter space or inflation. Epsilon equals 1 is flat space. Epsilon equals 2 is a radiation-dominated universe. Epsilon equals 3 is a matter-dominated universe. And there's some long story of finding a nice integral representation for this 4-point function. I'm going to study phi cube theory, but I claim that if we understand this integral, we actually understand any cubic vertex. So recall that now, because I relaxed the symmetry assumptions, even a 3-point vertex can be quite rich, unlike the case of flat space or de Sitter space. But we're studying phi cube theory, just like the same conformally coupled scalar everywhere in the diagram, this exchange diagram. And then you land in some interesting integral that you must compute. And we would like to understand how to compute this integral. It's not quite the bulk time evolution integral. It's like a massaging of it, but it's very much related to it. Notice that there are two integration variables. One called x1, the other called x2. And roughly speaking, they are related to the fact that there are two times that you must integrate over. And this is a function of the external kinematical data, and you'd like to bootstrap it or solve for its dynamics. So two questions is, how do I find a differential equation for this function f, and how do I solve it efficiently? Okay, so at least in this toy model, I'd like to be able to answer this question. And now here's the key point, the key observation. This 4-point function, it's an integral of it's a very simple integral. It has a rational integrand. In fact, this rational integrand is not any integrand. It's I'm calling it omega here. It's what it's called a canonical form. What it really is just some 2 form that has singularities along various lines, and on top of this when you hit these lines, you get logarithmic singularities. Okay, so just maybe as an example, if I have an interval, if I have one form, I have an interval that has only 2 singular points, minus a, minus b, and I would like to associate a canonical form to this interval. The canonical form for this interval would just be the x over x plus a minus the x over x plus b. So it's logarithmic, the one form and the 2 singular points, and the relative with residue 1, and the relative sign is determined by removing the pole at infinity. Okay, so this is the definition of a canonical form. If you never heard about it, just believe me, it's like some very special object with unit residues and logarithmic-like behavior around the singular points, multiplied by something that we're calling a twist, which is related to the fact that now you're in a cosmology that is power law. It looks very much like GMRAG in flat space amplitudes. And because the 4-point function is written in this form, then the strategy is to exploit the cohomology of the integrand. So now, because these are forms and they have logarithmic singularities, there is a beautiful theory of cohomology of these forms, and it's related to a whole machinery of amplitudes that I've been learning and enjoying very much learning about. For example, from lecture notes of Johannes Rehn, related to these types of integrands. So there's a whole technology that people use in the context of amplitudes to study loop amplitudes that turns out to be extremely useful to understand this cosmological correlator. Okay? So this is the key observation. And now here we go. So the first step is to actually enlarge the space of integrals that you're interested in studying. So you consider, instead of the case of the original integral, you consider, so here are the 5 lines in which the integrand becomes singular. And I'm plotting the lines here in the integration plane, x1, x2 plane. And the key idea is, here is the twist. I'm not going to touch the twist. And then the key idea is to consider these lines with arbitrary integer powers. And now you have, in principle, infinitely many of those integrals, parameterized by integer choices for all of these lines where the integrand becomes singular. And this theory of twisted cohomology, now it looks like a black box if you've never seen it before, but believe me, it turns out that the size of if you pick a basis of functions, so if you pick a certain subset of these f's here, then if you take a differential of these f's, differential with respect to the kinematical variables, it maps the f's onto themselves. Okay? And picking the basis is a bit of an art. And for this example, the right choice is to pick the canonical forms associated to the bounded regions. So these are the lines L1 all the way to L5 where the integrand becomes singular. There are 4 bounded regions. And in particular, the original 4-point function from cosmology that we were interested in is related to this bounded region here. But now there are 3 other bounded regions, and the idea is we're going to pick the basis to be twists times canonical form associated to all of these regions, okay? So this is the strategy. Looks a bit far-fetched, but it's actually a beautiful idea. So you form a vector, you're going to integrate the twists, but now against 4 different canonical forms. The top line of this vector is really the object that we were interested in. But then if you pick this choice of basis, then it turns out that this vector satisfies a beautiful, simple equation. It's like you find kind of an integrating factor for this vector psi. If you take a differential of the vector psi with respect to the kinematical variables, we call the big X1, big X2, then it's proportional to the size. But with this basis, not only that, it's linear in the twist. And the fact that it's linear in the twist is very useful. It's very analogous to people that know amplitude, is like picking this basis in which this becomes a fusion type of system. Very good. So now we traded all the dynamics of time evolution, yada yada, for this matrix A. This matrix A is really a magical thing. So I just want to state. So first, magic is that because it's proportional to epsilon, there are integrability conditions that this A must satisfy. In particular, it's flat and it squares to 0. This matrix A is a matrix that has components along the various directions in the kinematical space, and A wedged into itself is 0. Not only that, now the solution is trivial, right? Because d plus A psi equals 0, you just write the solution like this. And because this is a billion flats, this exponential is actually computable. But now the real magic is the form of the matrix A, which when I computed, I couldn't believe in it. And here it is. Just a reminder of the possible singularities of cosmological correlators. And A is a bunch of D-log forms. It's a D-log form of all the possible singularities of cosmological correlators. In fact, I had to make this slide a bit longer. With these spurious singularities that we don't like. But look at the entries. It's like 0, 1, minus 1 everywhere. And I had no clue of why. I still don't quite understand why. It's a bit operational. I understand why it happens, but I don't understand deeply why. So it's kind of a beautiful object. So here are some puzzles. So why are the entries only plus 1, 0, or minus 1? And this is a result of like some brute force computation. And so this matrix A is a very useful object, and we can write down the answer straight away once we know A. Can we apply this A for more realistic processes? Another thing that I find cool is that this matrix A is proportional to epsilon in the case of when people compute scattering amplitudes, and there epsilon is the Jim-Rag parameter. And here we are changing the infrared of the theory by changing the cosmology. So I don't know if this is just some interesting observation, if there's something deeper going on. The other thing is from the integral representation, I know how to find A. But if you hand me an A, I don't know if I can find some interesting integral representation for the entries. But the most fascinating thing, and that I'll spend the last couple of minutes discussing, is the issue of locality. Because remember, this system D plus A equals 0 is describing local process in space-time. So consider the following. So this is just some machinery to solve, to find the differential equation for a vector of canonical forms twisted by some twist parameters. So now consider the following thing, like a minimal modification of the integral. I'm just going to twist by another one of the singular lines. This is just another one of the lines in that plot, in this plot back here. So I'm just going to twist by the line L5 by the same amount. Okay. So this is just some mathematical formula. It has no space-time interpretation. And now look at the resulting matrix A. I'm color coding the entries that change under this twist. It looks completely ordinary. It seems to be nothing very different going on. And yet, if you study the system for the matrix A, you can massage it and land in local differential equations for the top row. Meaning you do something on the left and you collapse the 4-point function into some simpler object. Or you do something on the right and you collapse the 4-point function to something simpler. But now for A tilde, you find some homogeneous differential equation that has no space-time interpretation. You have to act with differential operators that depend on what's happening on the left, with coefficients proportional to what's happening on the right. So there's no locality in the story. So somehow the entries of this matrix A know about space-time locality. I have no clue of how to decode it. So I think it's kind of a beautiful problem. But okay, here's the outlook. I'm going to summarize. These cosmological correlators are really the building blocks of the initial conditions of the universe. To classify them, these differential equations are practically extremely useful. It's how we actually computed shapes that we couldn't do from brute force time integration before. And this new way of organizing the differential equations in terms of these flat connections, these matrices A, is extremely practical. And at least for this toy model, I showed you for the simplest diagram, but I think that now we know how to do it for any tree-level diagram. So can this machinery be applied to more practical or something more connected to cosmological observations? And it's also conceptually cool because somehow time evolution locality is all encoded in the structure of this matrix A. And of course, this machinery was developed for loops in flat space, so can it be applied also for loops in cosmology or for spinning particles and so on? So I think these are all fascinating questions, and I'll finish here. I'm happy to take questions.
Oh, thank you, DM. Are there any questions, either from the audience or via the chat? Sasha?
Hi, Guilherme. Quick question. So you say time evolution is traded in kinematic space. Is there a way to see that this time evolution was unitary? How do you see that it's a unitary time evolution?
I don't know how unitarity is encoded in the matrix A. Yeah, it's a good question. I know, given the answer, how to check for unitarity. There's some sort of version of the optical theorem applicable to this wave function of the universe. But if I stare at the matrix A, how do I know that it's coming from unitary time evolution? I don't know.
Thanks.
Any further questions?
So for amplitudes, we have a notion of transcendental waves, and it's also related to the odd forms. So do you have something like that here, or?
Well, maybe you have to teach me what transcendental weight is, because if, for example, if I send epsilon, okay, let's go back to, yeah, if I take this example and I send epsilon to 0, even though the system is d plus epsilon a equals psi, there is a meaningful epsilon going to 0 limit, and the solution is a dialog. It's a dilogarithm. So if you stare at this, maybe you can tell me that it obviously should have been a dialogue, but I don't know how to do it. Notice that naively, yeah, sorry.
So I was going to say the transcendentality of the answer when the epsilons are 0 is very manifest from the fact that the things that we're integrating are canonical forms of something. So they're polylogs of a particular weight, and they're even sort of exactly the kind of classic presentation, unlike for loops in amplitudes, where we have more integration variables naively than the transcendental weight of the object. Like at one loop, we have a d4L, but we get a dialog. Here, when the epsilons are 0, you have a classic sort of Aomoto-like presentation of polylogarithms. And there are even explicit formulas for the symbol that where the transcendental weight is exactly equal to the number of integrations over the vertices. When you turn on the epsilons, they're not polylogs anymore. These are sort of hypergeometric generalizations. That's the and again things that people are familiar with at finite epsilon in red. But the transcendental weight of these tree-level objects is highly manifest. And it's just given by the number of vertices that you're integrating with.
Is there a similar story for 3-point? If you jump to 4-point, is 3-point trivial? Or?
I suspect it's trivial because for 3 points, in the end, you have yeah. So if you play this game of bounded regions and so on, you find that for 3 points there's only one bounded region, and so the basis is one dimensional, and what you really find is the scaling of the integral. So what happens is that for various cubic vertices, you find different powers of the total energy that enters the vertex. So that's what you would discover if you run this crank.
And then can you use this fact? So when you have this D-log differential equation, you can expand it around the singular points, which some of the singular points, like you said, it's factorized into some like 3-point amplitude times then types have 3-point correlators. So maybe you can understand some of these matrices and these factorization limits.
Right. Yeah. That's a good question.
If I can make a comment, when the epsilons are 0, essentially that technique was what was used by Aaron Hillman to work out the symbol, to work out a recursive formula for the symbol. And there is also similarly, before that, there's another explicit formula, related ideas, it's not the same recursion relation, but just explicitly using the facet structure of the cosmological polytope to directly write down the symbol, which is exactly using the same kind of basic structure of the singularities and the factorization.
Right.
The kind of the very interesting story here is that this is there for totally general cosmologies, any epsilons, and that it differs in this sort of significant way that that it's really natural to think about these flat connections on kinematic space. And I think how precisely to think about how the singularities determine these hypergeometric functions. I think, in a sense, what Guy is showing us is just the sort of best way of doing it, and then translating these questions into properties of these flat connections.
Right.
But yeah, but I think but at epsilon equals 0, I think this is more or less a solved problem.
Right. And one last thing, one last comment is this was even studied by Johannes Hehn, I guess. You can take it's essentially so if you want to take one of these kinematical limits, it's essentially the matrix exponential of, say, only this matrix here that controls these kinematical limits. So you can access these singular limits quite directly from simple exponentiation of the constant matrices, in fact.
In view of time, let me wrap it up here, but let me also remind you that we do have the Slack channel if you want to continue the discussion. And let's thank Guilherme again.